Hey guys, how you doing? So we're going to be going over some things on alpha and beta decay reactions, because today you guys are going to be working on a nuclear equation worksheet which will deal with alpha and beta decay reactions. Okay, so yesterday we talked a little bit about this, but we didn't get kind of through the notes. So alpha decay is one of the processes that unstable atoms can use to become more stable. During alpha decay, an atom's nucleus sheds 2 protons and 2 neutrons in a packet that scientists call an alpha particle. So it's kind of like if you think about the snake's skin shedding, right? So it's going to shed off an alpha particle, and then you have the byproduct that's left over. So you have a byproduct of the alpha particle, and then you also have your byproduct of the element that's left over after subtracting that off, okay? And that's an alpha decay. Now, since an atom will lose 2 protons and 2 neutrons, during alpha decay, it changes from one element to another. So for example, if you have uranium-235 and I shed an alpha particle, that means I'm subtracting off an alpha particle. Alpha particle is a helium atom. So what I would do in this situation, I would say 235 minus the mass number of helium, which is 4, will give me 231. Then I will take the atomic number of uranium, 92, and I will subtract that from the atomic number of helium, giving me 90. And then I'll use my periodic table and I'll look up element 90, and then I will write the symbol, which happens to be thorium. So this is the full reaction of an alpha decay. Now, in a problem that you will get, I would only give you the isotope symbol that you start with. You would then draw your arrow. You would then, if it said it undergoes alpha decay, you would put in your alpha particle, subtract that from the original sample, and then whatever's left over, that's your byproduct, that's your element that's left over. Okay? Beta decay is a little bit different. On beta decay, a neutron turns into a proton and an electron. Okay? So the electron emitted is called a beta particle. This reaction would be written as follows. So if I started out with hydrogen 3, okay, and I said hydrogen 3 underwent beta decay, I'm going to do the same thing like I did with the alpha decay. I'm going to subtract off, but this time I'm going to subtract off a beta particle. And I had you write this down yesterday. A beta particle is an electron with no mass, with 0 mass, and a -1. Now, is that saying that electron doesn't have mass? No. It's saying that the electron's mass is so small that it doesn't contribute to the overall mass of the atom. Okay, so make sure you understand that. It's not saying that it has no mass, it's just saying that the mass is so small it doesn't contribute to the overall mass of the atom. So in this case, I'm going to say 3 minus 0 is 3, and then I'm going to say 1 minus a -1. So in essence, anytime you're subtracting a negative, makes it positive. So you're literally saying 1 plus 1 is 2. So now I have a helium-3 as my leftover byproduct. Okay? So in a situation like that, when you're subtracting off a beta particle, you have to remember that the beta particle contains a -1, so therefore you're adding a proton. Remember, you're not going to do anything to change the mass. The mass will stay the same. You're just adding a proton to the atomic number, okay? All right, so here's some examples of alpha emission, beta emission. Now, we won't be talking about positron emission and electron capture, but let's just look at a general example for a nuclear equation. Here's your original sample that you start with. A represents the mass number, and Z represents the atomic number, okay? So now, when I'm doing alpha decay, I'm subtracting off the helium. So I'm taking the mass number and I'm subtracting 4 from that because of the helium atom. I'm taking the mass number and I'm subtracting, the atomic number, and I'm subtracting 2. And that's what's left over here. And then you also have your alpha particle that you write. In a beta particle, okay, remember, because I have a -1 on my electron, you're in essence adding 1 to the atomic number, and the mass does not change. Okay? So here's some more examples. So in this particular situation, we have uranium-238, and it's going to produce thorium-234, and you have your alpha particle. In this beta emission, I have iodine-131, okay? I'm going to have xenon 131. And the reason it's xenon is because remember, when I subtract off that beta particle, it's going to add 1 to the atomic number. Okay? All right, so let's try these. All right, so an example here, what am I left with? Okay, so here I have radon-222, and it's undergoing a decay. So I can see right here that my mass reduced by 4 and my atomic number reduced by 2. So that tells me that I should write an alpha particle right here, which would be a 4 and a 2, and I would write helium. And then the decay type would be an alpha decay. Okay, looking at the second example, you have thorium-228 with an atomic number of 90. You still have 228, but now you have an atomic number of 91, which is palladium. So what kind of decay happened here? Well, we added a proton. So that means that my particle here should have been a beta particle. So I should have written a 0, a -1, and E for the electron, and the decay type would have been a beta decay. Okay? All right. So we will watch this video tomorrow. Not today, actually. I might push this video out to you in Google Classroom. It's just another way of looking at alpha and beta decay. But what you guys are going to be doing today is you're going to be doing alpha and beta decays. Please ask the sub for any assistance. He's more than qualified to help you guys on some of these reactions. Okay, I hope you have a good day.